So thanks for the invitation as well as the kind introduction. Now, I've made a small change in title compared to what was announced. As you'll see, what I'll be describing is not all that new, so I decided to call it relatively new. And also, when I wrote the abstract for the talk, I was hoping to explain two topics, but when I came time to actually prepare the talk, discretion seemed like the better part of valor, and I decided that one was enough. So with apologies, I won't be saying very much about the work of Maryam Mirzakhani on volumes of moduli spaces, except possibly at the end. Now, in the 1980s, several different approaches were developed to what you might call two-dimensional quantum gravity. I'll first recall one approach that involves a discrete approximation and the large n limit of a random matrix integral. So, well, here are some of the physicists who contributed, and later I'll say a little bit more specifically about what they did. So just to make a discrete approximation to geometry, you can consider, for example, a random triangulation of a two-manifold. So that's a piece of a two-manifold, which we've triangulated. And we've triangulated it with T triangles, where eventually T is going to be very large. And we consider each triangle to be, for example, an equilateral triangle with a side of some fixed length A. And then we're going to try to take a limit where A goes to 0 and T goes to infinity, hoping that random triangulations will converge to some kind of limit that will be a reasonable model of two-dimensional quantum gravity. So very concretely, to study this, you count triangulations of a given two-manifold with T triangles, where T is supposed to be very large. And the answer will have a term that grows exponentially with T. Well, that term isn't interesting because T is the area of the surface. So, okay. T is divergent because A is going to 0 and T is going to infinity. But what that actually means is that you eliminate that divergence by renormalizing the cosmological constant. You're more interested in subleading terms like a power of T and subleading terms beyond that. So as I just said, you renormalize away the leading exponential, but underneath it, you look for universal behavior from which you hope to extract a model of quantum gravity. So if you like, we could have used squares instead of triangles, and then the claim is that C would be different, but S would be the same. You're interested in the features that don't depend on the precise procedure. So then the physics is in these subleading terms that you don't get rid of when you cancel the leading exponential. Now, actually, it's a little more convenient to consider not the triangulation, but the dual triangulation. So in black is our original triangulation, and then here in red is the dual triangulation. So the original triangulation was built out of triangles, but it had vertices of all orders. For example, in the black picture, 6 lines meet at this vertex. By going to the dual triangulation instead, triangulation is the wrong word for the dual. By going to the dual covering, we now have only trivalent vertices, although we have polygons of all orders. And it's, as you'll see in a second, it's convenient to have simple vertices. So now what we're talking about are trivalent graphs that can be drawn on a given two-manifold. Now, there's a very simple way to count trivalent graphs if you don't care about using them to triangulate a two-manifold. So you just look at this integral, which depends on a parameter lambda. As written, it's a little bit divergent. Well, we could make it converge by integrating on the imaginary axis. We could slightly modify it to make, oh, we could put an I there, actually. Well, we could simply say that lambda is imaginary. Then it converges. But we don't care about that because we're just going to make an asymptotic expansion. So if you've studied Feynman diagrams a little bit, then you know that when you expand in powers of lambda, you'll generate Feynman diagrams with cubic vertices. That is, trivalent graphs. And, oh my goodness. Yes, you're correct. Thanks for pointing that out. This is a very important typo. That's definitely meant to be x cubed. Right. Okay. Unfortunately, I can't easily correct it in real time. But imagine that's x cubed. And then if you know your Feynman diagrams a little bit, when you expand it in powers of lambda, you'll generate trivalent graphs. Feynman diagrams with cubic vertices are trivalent graphs. And the propagator is actually 1. So the integral just counts trivalent graphs. Well, it counts them with a correction due to the fact that they might have symmetries. So each one is weighted with 1 over the order of its symmetry group. However, a generic trivalent graph doesn't have any symmetries. So roughly speaking, you just count trivalent graphs. Now, these graphs aren't quite what we want since they're abstract trivalent graphs, not triangulations of a two-dimensional surface. So there I've drawn a trivalent graph, and it's not particularly nice to regard it as a triangulation of a surface, a covering of a surface. You could find some surface in which you could draw that graph. But this integral will generate all trivalent graphs, irrespective of what kind of two-manifold you could put them on. So it's not what we want, but anyway, let's just finish with the counting problem. And this time I see it is x cubed. So abstract trivalent graphs are easy to count because the number of trivalent graphs with v vertices is just the coefficient of lambda to the v in this integral. So expanding the exponent in powers of lambda, you just find that the number c sub v of such graphs is this integral, which actually is an easy integral to do in closed form. But if you couldn't do it in closed form, you'd say that for large v, you would just look for the maximum of the integrand. And it would actually have a sharp saddle point for large v. So you don't really need the fact that you can do it in closed form. Now, what we want to count are not abstract trivalent graphs, but graphs drawn on a fixed two-manifold. So here maybe we should be more specific about what a fixed two-manifold is. We'll take closed, oriented Riemann surfaces without boundary, and therefore with some given genus. So it might have genus 0, it might have genus 1. But anyway, we'll be discussing compact-oriented two-manifolds without boundary. And we want to triangulate one of them, or draw a trivalent graph on it. So how to count trivalent graphs, not abstract trivalent graphs, but trivalent graphs on such a two-manifold, was explained by Hooft a long time ago, actually when I was a graduate student. You simply replace the real variable x by an n by n Hermitian matrix M. So what we did before was the case n equals 1, where the Hermitian matrix is just a real number. And you write the same, well, you write a matrix version of the same integral we had before. Now, when you expand in powers of lambda, the coefficients are functions of n. And you really should expand in powers of lambda and 1 over n. And at Hooft's result, basically, is that the coefficient of lambda to the v times n to the 2 minus 2g is the number of trivalent graphs with v vertices that you can draw on a Riemann surface of genus G. Now, so if you simply take the large n limit, that's like setting G to 0. As was first shown by these authors in 1977, if you want to simply take the large n limit, you can do that by random matrix methods that go back to Wigner, Dyson, Mehta, and others. Now, the contribution of the physicists I cited at the beginning was to show you can do something more delicate. So this was in 77. But then in the 80s, the people I listed at the beginning explained that you get a more interesting result if, while taking n to infinity, you adjust lambda to a critical value at which the perturbation expansion ceases to converge. So that's the critical value at which the typical number of triangles goes to infinity. So maybe I should explain that in the n equals 1 version of this problem, the integral, if we said n equals 1, so we're just doing a real integral, there's actually an essential singularity at lambda equals 0. So we can make an asymptotic expansion, but that's all we can do. If we take the large n limit, then the coefficient of each power of n is actually an analytic function of lambda near lambda equals 0. So it's an honest function. It's not just an asymptotic series. And what was found is that you get the most interesting result at the boundary of convergence, or at the singularity closest to the origin of that function. And at that point, the perturbation expansion diverges, and there's a scaling limit in which the number of triangles in a typical triangulation, if I go back to the original picture with triangulations rather than trivalent graphs, the number of triangles diverges, and you get what's believed to be a good model of two-dimensional gravity, two-dimensional quantum gravity. So it's quantum simply because the geometry is random. So the model is solvable in this limit, and the solution was given almost 30 years ago by 3 groups. Now, that's about as much as I'll be able to say about this approach at the moment, because we have to go on and explain some other things. So I'll have to say even less about a second approach to two-dimensional gravity. A second approach is a conventional bosonic string with the matter system taken to be alluvial field with its coupling adjusted so the central charge C is 26. So the importance of that value is that it's where the anomalies cancel. This is related to the fact that the critical dimension of the bosonic string is 26. So you could replace the standard bosonic string with what proves to be a much simpler model with only a alluvial field of C equals 26 instead of a 26-dimensional spacetime. And then, it's a much simpler model. It's a conceptually interesting framework, and it puts the subject in the framework of string theory. It doesn't lead in any obvious way to a simple method to calculate. But in the late 80s, very strong evidence was found that the result from this approach is actually equivalent to what you get from the matrix model, from the random matrix integral and the random triangulations. So, this is often described by saying that the matrix model solves the string theory with the alluvial field. So, this relationship enables you to solve the alluvial theory that you otherwise couldn't solve, and it makes the matrix model a part of conventional string theory. Unfortunately, we don't have time for this approach today, mainly because the relatively new development I wanted to tell you about isn't in that direction. There's a third approach, which was also found to be equivalent to the first two, that I want to describe today. So this involves intersection theory on the moduli space of Riemann surfaces. So now, we consider a Riemann surface of genus G with n marked points or punctures that I'll label as x1 up to xn. So here I've drawn a genus 2 surface with 3 marked points. And MG, you should think of it as a complex Riemann surface, or equivalently a 2-manifold with a conformal structure. And MGN is the moduli space of complex or conformal structures on this 2-manifold. Then, if you're living at a point on this 2-manifold, it's got a tangent space, or equivalently a cotangent space, which is a 2-dimensional real vector space, or equivalently a 1-dimensional complex vector space. And I've called here that 1-dimensional complex vector space Wi at the ith marked point xi. And it's well defined for any complex structure on our surface. But as you move around, as the surface sigma moves around in its moduli space, W will vary as the fiber of a complex line bundle, Li, over the moduli space. So for each marked point, you've got a line bundle over the moduli space, which is simply the fiber at that point of the complex cotangent bundle to that point in the Riemann surface. Well, a complex line bundle has a first Chern class, and I'll write psi I for the first Chern class of L sub I. And then the correlation functions of 2-dimensional topological gravity are the intersection numbers. So you take n marked points over MGN parameterizes a surface with n marked points. And then for each marked point, you've got a 2-dimensional cohomology class psi sub I. So you take psi 1 to the A1, psi 2 to the A2, and so on, up to psi n to the AN, where the A's are positive integers chosen so that this expression is a cohomology class of top degree, which would be degree 6g minus 6 plus 2n. Then if that's true, you can integrate it, and you get a number. And those numbers are the intersection numbers of what I'll call topological gravity. So here I should say that technically by MGN, I really mean the Deligne-Mumford compactification of the moduli space. So in that sense, and these line bundles are all naturally defined. These classes all naturally extend over that compactification. So MGN then is a compact manifold without boundary. So, moreover, it's oriented by its complex structure. So the integral of a product of cohomology classes, such as the psi I, is a well-defined topological invariant. You don't have to say anything about putting any further structure on your surface. This is a well-defined number, actually a rational number, not an integer, because MGN is an orbifold. And these rational numbers are the intersection numbers, sorry, the correlation functions of topological gravity. So I conjectured that this intersection theory is equivalent to the other two approaches. I won't state the conjecture precisely, but in an slightly oversimplified version, the correlation function we had on the previous picture, this expression, is supposed to equal what in the matrix model would be the expectation value of a product of traces of the matrix. So basically, that's the relationship between the matrix model and the intersection theory. So this conjecture was proved in the early 90s by Kontsevich with a very clever trick where he introduced a new kind of matrix model to prove this conjecture. And a little over a decade ago, Maryam Mirzakhani, actually as a student, constructed a very elegant new proof which involves studying the volumes of moduli spaces with the Weil-Petersen symplectic form. And that's the second topic that I was hoping to squeeze into this talk when I gave the abstract, but which I decided would be too much. So I won't really be explaining that. So instead, I'll tell you about another side of the story. So what happens if the surface sigma has a boundary? So sigma is a two-manifold, which will continue to take to be oriented. But what if sigma is an oriented two-manifold with boundary? Well, in the approach based on triangulation, I wrote triangulations of moduli space, but I meant triangulations of sigma. Just forget this phrase of moduli space. In the approach based on triangulations, there's no problem. There's no difficulty to triangulate a Riemann surface with boundary. Here's a picture. The red line is the boundary of a two-manifold. The two-manifold is to its right, and we've triangulated it, or at least we've triangulated a piece of it. And then we can do the same thing to clear all those triangles or equilateral triangles, even though they don't look like it on the screen. And that gives a random geometry, and we try to take the same limit as before. So the starting point for triangulations has no difficulties if the two-manifold has a boundary. Now, it's a little more subtle in the matrix model language, but there's actually no problem to find a matrix model that counts triangulations of a Riemann surface with boundary. You just have to add what people in this field call vector degrees of freedom. That is, in addition to integrating over the matrix, you integrate over additional variables that live in the vector space that the matrix can act on. So the additional variable is a column vector or a row vector instead of a matrix. And the additional variables could be either bosons or fermions. So you add, so psi, let's say, is a column vector, psi bar is a row vector. You add vector variables, and you integrate over m, psi, and psi bar. The same thing you had before, except that you couple the column vector, column vector and the row vector to the matrix. But now you can introduce one free parameter. And it's interesting that you can introduce one free parameter in a natural way. So we couple it actually to m minus u. Now, equivalently, you can do the integral over psi and psi bar, which is just a Gaussian integral. And for example, if psi and psi bar are fermions, the result of the Gaussian integral is the determinant of m minus u to the +1 power. For bosonic, for ordinary, if psi and psi bar were complex variables, in other words, bosonic variables, you'd get the inverse determinant. So they're different models, but well, they would both be regarded as good models. They actually differ by whether in the sum of random geometries you want to include a -1 for every component of the boundary. So people doing two-dimensional gravity would consider each model equally sensible, but for example, we could do this one. So here I've explained it in a language where you don't talk about the vector degrees of freedom, but well, to just write down the determinant out of the see, if you go to this picture and expand it in perturbation theory and study your Feynman diagrams, after a little while you'll discover trivalent graphs drawn on a two-manifold with boundary. So this picture is better for explaining the connection to the random triangulations. This version might be easier for some computations. Now, it's also relatively clear, though possibly a little more subtle, how to incorporate boundaries in the string theory description. In other words, in the description by the Liouville field of C equals 26. You basically just need a boundary condition for the Liouville field, or in the jargon, you need to find the brane for the Liouville field. So a Liouville field is a scalar field that obeys not the Laplace equation, but a nonlinear equation, where the Laplacian of phi plus e to the phi is 0. But trying to find a boundary condition on it is very much like trying to find a boundary condition for an ordinary scalar field. And there's a version of Neumann boundary conditions that make perfect sense. There are different things you can do. But related to what I've told you in the other picture, what you want to do is Neumann boundary conditions. And if you take Neumann boundary conditions, there's one boundary parameter, which people call the boundary cosmological constant. In string theory language, it's the coefficient in the action of a term proportional to the length of the boundary. So, so in the matrix model, we had one parameter. And in the Liouville picture, there's again one parameter, which here is the boundary cosmological constant. But what happens in the approach based on topological gravity? Well, there's a bunch of things that are going to go wrong, and how to fix it is the main point of the seminar, actually. But before explaining everything that goes wrong, let's tell you something that goes right, just so you'll think it's worth trying to slog through the difficulties. So here I've drawn a Riemann surface with boundary, and now we presumably want to consider boundary punctures as well as bulk punctures. But there's a fundamental difference between a boundary puncture and a bulk puncture. A bulk puncture has got a cotangent bundle, which if you view it as a complex line bundle, is a non-trivial complex line bundle, and that's because there's no preferred direction coming out of this point. A preferred direction would tell you how to trivialize that complex line bundle and make the first Chern class vanish, but it was born without such a preferred direction. But if you're living on the boundary, there's actually a preferred direction. Remember, this is an oriented surface, so the boundary is also oriented and has a preferred direction. And that preferred direction on the boundary trivializes the cotangent bundle of the boundary mark points. So there's no interesting line bundle or cohomology class that we can associate to a boundary puncture. So we can specify the number of boundary punctures, but then we don't we have the variable, the observables, observable with the physics language here, the observable psi I, the first Chern classes of line bundles, associated. So at any bulk puncture, we can associate our favorite power of the observable psi, the first Chern class. But there's no corresponding observable for a boundary puncture. So when we introduce, let's say, n prime boundary punctures as well as n bulk punctures and h holes, what we integrate will be the same as before because there aren't any new analogous classes for boundary punctures. So we'll simply integrate the same cohomology classes as before, but on a different space, which now parameterizes conformal structures on a genus G surface with h holes, n bulk punctures, and n prime boundary punctures. So that's a formal recipe. We'll discuss what's wrong with it in a moment. So formally, we're integrating the same thing, but the space in which we're trying to integrate it is different. Instead of mgn, we have this mgn n prime h, which parameterizes all this stuff. Now, there's something nice about that result, the fact that there were no boundary observables. So it means that adding boundaries will add precisely one new parameter the theory depends on, which in physics language you can call the fugacity for boundary punctures. Mathematically, what it means is that, well, the theory depends on an integer, which is the number of boundary punctures, but it's more convenient to add up all those integers and make a generating function. So you'd sum over the number of boundary punctures, weighting the case with n prime boundary punctures with, let's say, u to the n prime, where u is a new variable. So then the theory summed over all the choices depends on one more parameter. And that's a good candidate for being dual to the one parameter that was seen in the matrix model and the Liouville theory. In the matrix model, there was u, where we took the determinant of m minus u, not the determinant of m. And in Liouville theory, there was the boundary cosmological constant. Here, although the explanation was different, again, it's natural to have one more parameter when you have boundary punctures that simply counts the boundary punctures, and there's nothing else you can do of a topological nature. Or there's nothing else that's similar in spirit to what we did for the bulk theory. So by contrast, for bulk punctures, there are infinitely many parameters. In matrix model language, you have infinitely many observables, trace of m to the n, and you can add them to the action with arbitrary coefficients. That would be the infinitely many parameters. Alternatively, you have different kinds of bulk. In the topological language, a bulk puncture is labeled by a positive integer n. And you might want to keep track of how many bulk punctures are labeled by n. And so you'll make a generating function that depends on a variable, but it will be a variable for each n. So infinitely many variables. But adding boundaries only adds one more variable in each of the three approaches. So that's the good news, and it's the only good news we'll have for a while. Because at first sight, and even at second sight, the correlation functions we wanted to define look like they don't make any sense. And the first problem is that the moduli space of Riemann surfaces with holes is actually unorientable. And you can't integrate a differential form on an unorientable manifold. There are things you can integrate on unorientable manifolds, but you can't integrate differential forms. And here, we want to integrate precisely these differential forms because that's what we did when the two manifold was orientable. And we were trying to generalize the theory in a smooth way. So that was what we did when there was no boundary, and we want to generalize it in a smooth way without changing anything to allow boundaries. So we have a problem that the moduli space is unorientable. So we can't make sense of the correlation functions. I want to explain why the moduli space is orientable. So here I'm going to compare a Riemann surface, which I took to have genus 1, with a puncture, or mark point, to one with a hole. So when I add a puncture, I add two real moduli, which are, let's say, the real and imaginary part of the position of the puncture. If I add a hole, I add three real moduli. You can think of, if the hole is small, you can think of the moduli as the real part and imaginary part of the position, but there's also the size of the hole, which is a real parameter. So, now, adding a puncture to a complex Riemann surface doesn't affect the orientability of its moduli space, because there's no problem in the sign of a two-form dx bar associated to the extra moduli. If the moduli space was orientable before, it's still orientable if you take a fiber bundle by adding one more puncture with orientable fiber. Now, similarly, for one hole, there's no problem because we can write a three-form dx bar dB. And that's a kind of relative, that will give us a relative orientation of the moduli space with the one hole compared to the moduli space without a hole. The problem comes with two or more holes. So with two or more punctures, for each puncture we add a two-form dx bar, and two forms are bosonic, they commute, it doesn't matter how to order them. But for holes, we have a three-form dx bar dB, and three forms anti-commute. So these anti-commute for different holes. So to try to give a relative orientation of the moduli space, in other words, or to orient the moduli space with holes, given what you know when there aren't holes, you need to know how to order the holes modulo an even permutation. So there's no natural ordering of n objects up to an even permutation, so we're in trouble. And we're actually in even worse trouble for the following reason. If a Riemann surface sigma has two or more holes, it'll have a diffeomorphism that exchanges two holes, preserving the orientation of the surface. And exchanging two holes will reverse the orientation of the moduli space because it will exchange two of our three forms. So our moduli space doesn't just lack a natural orientation, but it's actually unorientable. So that's pretty bad, but there's actually another problem. So MGN with only punctures, or mark points, but no boundaries, is a manifold without boundary. And that's important in the fact that the correlation functions are well defined. So the integral of a product of cohomology classes on a manifold without boundary is well defined. But once you allow holes, MGNH is a manifold with boundary. And that's bad news because, in general, you don't know how to integrate a cohomology class on a manifold with boundary. You would need a trivialization on the boundary, which is hard to come by here. So I wanted to explain why MGNH is a manifold with boundary, but I ran into the limits of my artistic talents. So I'm not sure the picture will be very clear. This is meant to be a piece of a two-manifold that's developing a long neck. And the two-manifold can degenerate by the neck becoming very long or by the circumference going to 0. But that degeneration is in real codimension 2. It's not a boundary. It's actually a complex divisor in the compactification. Because to the neck, you can associate both its length and also a relative twist, a rotation of one end relative to the other, which is information that you would lose if this neck collapses to a singularity. So the collapse of a two-manifold to become singular is real codimension 2. Now, this here is meant to be a two-manifold with boundary, where this is the upper boundary, this is the lower one, and the two-manifold is literally a piece of the screen. So I'm not sure what this looked like, but here you're supposed to imagine that you're simply looking at a piece of the screen bounded by this and by this. And now, we could let the narrow neck here become, we can let its width shrink to 0, or equivalently, conformally, we could let the distance through here go to infinity. They're equivalent conformally. But either way, that happens in real codimension 1. And that's a boundary of the compactified moduli space. So with holes, the moduli space has a boundary, although without holes, it does not. And that's bad news, because you can't integrate a cohomology class on a manifold with boundary in general. So, well, okay. These were long-standing problems, which, well, I didn't understand them as well as I do now, but I certainly had some idea of the difficulties back in the old days, and eventually gave up, not knowing what to do. I worked on other things. But I was quite surprised when a couple years ago, Pandharipande, Solomon, and Tessler solved this problem with a proof being completed in another paper by Buryak and Tessler. So they gave a satisfactory definition of the open string correlation functions of topological gravity. That is, they found an appropriate substitute for our naive definition. And they showed that their correlation functions satisfy closed analogs of all the usual equations in the more familiar case of closed Riemann surfaces. So I haven't had time to tell you about any of these usual equations, but it's a very rich story with KdV equations, Virasoro constraints, and topological recursion relations. Anyway, all the things I didn't have time to tell you about, these authors showed have analogs for Riemann surfaces with boundary. So Robert Dijkgraaf and I, in a forthcoming paper, will compare their answer to the matrix integral that I described earlier for a Riemann surface with boundary, where we had the determinant. And we'll also describe what they did in a somewhat more physical language. And the second part of that sentence is what I'll do in the rest of the time today. Well, in physics language, you might say that the unorientability of the moduli space is a kind of gravitational anomaly. So the diffeomorphism that exchanges two holes has the unfortunate property of changing the sign of the integration measure of our quantum theory. So our measure was not invariant under a certain diffeomorphism that's not connected to the identity. Bad news. So the gravitational sector has an anomaly. But when that happens, physicists are supposed to know what to do. You find a matter system that cancels the anomaly. The only trouble, well, first of all, in the present context, the matter system is going to have to be a two-dimensional topological quantum field theory. But it's going to have to be one that's almost trivial in the following sense. On an orientable, I wrote orientable Riemann surface, but I meant orientable Riemann surface without boundary. On a Riemann surface without boundary, we had a satisfactory theory that we don't want to change. We could change it and study some other theory, but the goal here is to take the theory we already have and extend it to Riemann surfaces without boundary. So whatever matter system we add has to have the property that it does nothing on an orientable on a Riemann surface without boundary. Well, to be more exact, the matter system should be trivial up to a renormalization of the string coupling constant, G string. A G-loop amplitude is proportional to G string to the 2G minus 2, where G is the genus, G string is the string coupling constant. So that's been hidden in my presentations. I didn't even introduce a generating function that depended on all the variables, but if we had, a redefinition of one of the variables would have multiplied our answer by c to the 2g minus 2 for an arbitrary positive constant c. So our matter system doesn't have to be completely trivial on a Riemann surface without boundary, but it has to have the property that it can be, whatever it does has to be of the form c to the 2g minus 2 for a fixed constant c, independent of g. And then that will give us a matter system that we could introduce without changing the theory on a Riemann surface without boundary. So what kind of topological field theory that will do something interesting when there is a boundary is as close as this to being trivial without a boundary? Well, so it has to have a partition function on a genus G closed surface of the form c to the 2 minus 2g for some c. Well, the answer turns out to be, in part, that sigma must be endowed with a spin structure. So we actually will be studying a Riemann surface with spin structure. In 2 dimensions, there's a rather trivial topological field theory in which you simply sum over spin structures, weighting each one by a factor of 1/2. The reason for a factor of 1/2 is that a spin bundle has an automorphism plus or minus 1. It's a double cover. The structure group is a double cover of the structure group of the tangent bundle of the surface. And the double cover introduces plus or minus 1 as a kind of gauge transformation. So when we integrated over moduli space, we've already divided by diffeomorphisms. But when there's a spin structure, a diffeomorphism only has a well-defined action up to plus or minus 1. So the volume of the group we have to divide by is twice as big now. So for the matter sector, we just sum over spin structures, weighting each one by a factor of 1/2. Where that's a discrete version of the Fadeev-Popov gauge fixing. And 2 is the number of automorphisms of a spin structure. So let's see if this very simple TQFT has the property that its partition function is a constant to the 2 minus 2g power. Well, in genus G, the number of spin structures is 2 to the 2g. So the partition function of this trivial theory is a half of 2 to the 2g, and that is 2 to the 2g minus 1. It's not 2 to the 2g minus 2. So it's close, but no cigar. It's not of the form c to the 2 minus 2g for any c. So we need something else. Now, there is something else we can do that's deceptively close to being equally simple. Well, you'll see when we proceed, you'll see that the other theory wouldn't have worked because it wouldn't have had an anomaly. But on a surface without boundary, we can say that a spin structure is either even or odd. I'll give a definition of even and odd in a moment. But there's a topological field theory in which spin structures are weighted by an extra factor of minus 1 to the w, where w is 0 or 1 for an even or odd spin structure. The partition function is then half times the sum over all spin structures of minus 1 to the w. The number of even spin structures is this, and the number of odd ones is this. And half of the difference of those two numbers is this. And that is something to the 2g minus 2 power. So now we're in luck. So this is a conceivable candidate for a matter system that we could add to the theory without changing it on a Riemann surface without boundary. But the theory with the factor of -1 to the w included has an anomaly or a problem on a Riemann surface with boundary, which is good news, of course. So to explain why there's a problem, we need to define w, and here's one way to define it. So let d slash be the Dirac operator acting on spinors on a Riemann surface, and d slash plus be the Dirac operator on positive chirality spinors, which maps to negative chirality ones. So in algebraic geometry, d slash plus is the d-bar operator acting on k to the 1/2, where k is the canonical bundle. So w is the number of zero modes, in other words, the dimension of the kernel of d slash plus mod 2. So you can show that the dimension of the kernel, the number of zero modes, is a topological invariant mod 2. You roughly simply use Fermi statistics to prove, or anti-symmetry, if you like, of the Dirac operator to prove that when the metric or complex structure on the surface is varied, zero modes can only appear and disappear in pairs. But anyway, it's classical algebraic geometry that there's this mod 2 invariant. So this definition makes sense and gives a topological invariant. Well, it's not exactly a topological invariant. It depends on the spin structure. If sigma is a Riemann surface without boundary. But my definition doesn't make sense if sigma has a boundary, because then any local boundary condition, well, to get an elliptic Dirac operator whose zero modes you can count, you want a local boundary condition, and any local boundary condition mixes the two chiralities, so then it no longer makes sense to talk about the kernel of d slash plus. You only have a combined Dirac operator that combines d slash plus and d slash minus on a closed surface that would have multiplied the dimension of kernel by 2 and eliminated your mod 2 invariant. There are non-local elliptic boundary conditions, but with such boundary conditions, W is not a topological invariant. Now, the fact that the good definition doesn't make sense when sigma has a boundary suggests that -1 to the W has an anomaly in that case. But to go more deeply, it helps to have a physical realization of the factor -1 to the W in the partition function. So for this, we introduce on sigma a pair of massive Majorana fermions, chi1 and chi2. And the partition, well, I'm going to write the formulas in a deceptively simple way to avoid explaining some distracting details. So I'm cheating slightly. But the partition function of either one of them is a Pfaffian of the Dirac operator plus the mass. And that Pfaffian is naturally real, but its sign is actually hard to define. The sign of a single such Pfaffian has a subtle anomaly. But for a pair of such fermions, there's no issue with the sign. For example, if they have the same sign of the mass parameter, the partition function is the square of the Pfaffian. The Pfaffian was real, so its square is real and positive. And not only is it real and positive, but it's trivial at long distances or for large m, in the sense that being massive, the fermions at long distances, or from a long distance point of view, only contribute some renormalizations that here are inessential. They renormalize the cosmological constant and the coefficient of the Euler term in the action, which you could think of as the string coupling constant. So after renormalizing a couple of parameters, this partition function is not just real and positive, but it's trivial. It's 1. So trivial means that the partition function is 1. It doesn't matter whether you include this pair of fermions or not, after suitably renormalizing the parameters. So this is the theory in which you just sum over spin structures with no sign. The more interesting case is where chi1 has a mass parameter of 1 sign, and chi2 has a mass parameter of the opposite sign. The partition function is then a product of two different Pfaffians. And this is a well-defined real number, because in general, anomalies are independent of masses. So since we argued it was well-defined when the masses were equal, it's still well-defined when the masses are equal and opposite. It's a well-defined real number, but it's not necessarily plus 1. You can flip the sign of the mass of one of them and reduce to the previous case by discrete chiral rotation, but this discrete chiral rotation has an anomaly which can be measured by counting the zero modes of the Dirac operator. And the anomaly gives a factor of -1 to the w in the partition function. So finally, the theory with equal and opposite masses, after some trivial renormalizations of the cosmological constant and the string coupling constant, gives you our theory where we're supposed to sum over spin structures with an extra factor of -1 to the w. So, okay, this will be a useful interpretation of that theory. Now, before going on, I want to point out that this theory, with the -1 to the w, is actually important in contemporary developments in condensed matter physics. So, well, this theory is known as the Thekitaev's Majorana spin chain. So the claim to fame of Thekitaev's spin chain is that for a very long but finite chain, there's a Majorana zero mode at each end of the chain. So the claim is that a gapped fermionic chain, that is a chain of fermions, with no symmetries assumed except that fermions are conserved mod 2, has two possible gap phases, a trivial one and a non-trivial one with a Majorana zero mode at each end of the chain. And I've told you about these two phases in a sort of abstract language where we include a factor of 1 or -1 to the w for each spin structure. Well, now let's look at what happens when sigma has a boundary. Well, in condensed matter, of course, the effective boundary condition will be such that the theory is completely anomaly-free, even on a manifold with boundary. That just says that, that was a fancy way to say that condensed matter systems that you can make in the laboratory are well-defined. Now, to make something which is well-defined, it suffices to give chi1 and chi2 the same boundary condition. And remember, the boundary is a one manifold, so it has one gamma matrix, which I'm calling gamma parallel. And the boundary condition can be that chi is an eigenstate of gamma parallel with eigenvalue either 1 or -1. You can make your favorite choice. It doesn't matter as long as you make the same choice for each. If you make the same choice for each, the partition function is still the square of a real Pfaffian, so it's still positive definite, even on a manifold with boundary. And after some trivial renormalizations, the low-energy theory is completely trivial. But we're interested in the case where chi1 and chi2 have mass parameters of opposite sign. And I want to contrast what happens in condensed matter physics with what we need. In condensed matter physics, well, first of all, as I said, the theory is still anomaly-free. So we're going to now keep the boundary, but with this anomaly-free boundary condition. So both fermions have the same boundary condition. But we now take them to have mass parameters of opposite sign. The theory is still anomaly-free because masses don't affect anomalies. But if you solve the Dirac equation, you'll find that either chi1 or chi2, but not both, has a Majorana zero mode along the boundary. Which one it is depends on which choice of boundary condition you made. So I won't do the computation for you. I was tempted, but I was worried it was too much to squeeze in. But it's more or less Thekitaev's original derivation of the edge mode of his Majorana spin chain. Now, for our problem in two-dimensional gravity, we don't want to do what one would do in condensed matter physics and study a matter system that's completely anomaly-free. Our gravity system had an anomaly, and the reason we're talking about a matter system is that the matter system is supposed to be anomalous to cancel the original anomaly. Also, we don't want to get fermion zero modes along the boundary because then our correlation functions would vanish. We'd have no way to get rid of those zero modes. So in condensed matter, you can hope to measure those zero modes in the lab, but in topological field theory, we'd be out of luck, stuck. Now, the theory was anomaly-free when chi1 and chi2 had the same boundary condition. So to have an anomaly, we want chi1 and chi2 to obey opposite boundary conditions. So now we take chi1 and chi2 to obey opposite boundary conditions and also opposite masses. Then the path integral of the chi1, chi2 system is genuinely anomalous. The anomaly only involves a sign, just like the gravitational anomaly we're trying to cancel. So the orientation of moduli space, which was our anomaly, is only a question of a sign. This is also only a sign, because if we double the chi1, chi2 system, it would become trivial again. Then we'd have pairs of fermions with identical masses and boundary conditions. So we have a system that has an anomaly only in the sign. After trivial renormalizations, it's of modulus 1, but the sign isn't really well defined as a real number. The fancy mathematical language is that the partition function is a section of a real line bundle, which measures the anomaly. We can call the partition function -1 to the w, but w is no longer a well-defined number mod 2, 0, or 1. It's a slightly more abstract type of beast. But now we can make an improved version of the definition of the correlation functions. The improved definition is the same thing as before, but we sum over spin structures, divide by 2, and include a factor of -1 to the w, where we've included -1 to the w in hope of canceling the gravitational anomaly. Well, there's a point that's slightly too technical to explain now fully, but the inclusion of the factor -1 to the w doesn't quite cancel the gravitational anomaly, but only reduces it to something more elementary. The line bundle in question becomes a tensor product of a separate real line bundle for each hole. So the anomaly becomes local, whereas before it was not local. So we've gained something, but we're not finished. So we're still missing an important ingredient in the story of Pandharipande et al. And I don't want to do a technical computation of the anomaly to explain what's missing, so instead I'll give a heuristic explanation. If sigma is a Riemann surface with boundary and with a spin structure, then its boundary components are either Neveu-Schwarz or a Mon type in string theory language, which has to do with whether the spin bundle restricted to the boundary is a trivial or non-trivial real line bundle, or whether it's bounding or non-bounding, or whether fermions are antiperiodic or periodic in going around the boundary. I hope one of those characterizations made sense for most of you. But for topological reasons, the number of Riemann boundaries is always even. So if sigma has only a single boundary, it's necessarily of Neveu-Schwarz type. So here's a disk. It's supposed to be filled in inside, with its unique spin structure, which has a Neveu-Schwarz boundary. And I've drawn some boundary punctures. In fact, I drew 5 of them. Well, the dimension of the moduli space of conformal structures on such a disk with n boundary punctures is n-3, where the n is the positions of the n punctures and -3 is for dividing by SL2R. Now we note that n-3 is even if and only if n is odd. The reason we'd like n-3 to be even is that what we're trying to integrate are some even degree cohomology classes, because the size are all of even degree. So if the moduli space has odd dimension, it'll be no good. We can't use it. So odd-dimensional moduli spaces won't play a role in this theory. Now, presented with this, you could imagine that the odd-dimensional moduli spaces exist, but you don't use them. Well, that's not what happens in the theory of these people. The theory is set up in such a way that the odd-dimensional moduli spaces don't exist. And that's achieved by slightly changing the definition of what it is that you parameterize by this moduli space. But what you have to say, although it's actually very simple, is a little bit elusive and will sound abstract the first time you hear it. So the boundary of a Riemann surface is one-dimensional, so it has just one gamma matrix, gamma parallel that we used before. And a spin bundle is achieved by finding a representation of the gamma matrices. But if you only have one gamma matrix, you can represent it by 1 or -1, whose square is +1. So a spin bundle is a real line bundle, a real vector bundle of rank 1. And in general, a real line bundle over any topological space can be trivialized locally in two ways, up to homotopy, by saying what's the positive direction in the fiber. So you have a real line which comes with an origin, but nobody told you what's the positive direction. But you can decide. You can pick up or down as the positive direction. Once you've picked the positive direction, up to homotopy, you've made that real line bundle trivial. And locally, on the boundary of a Riemann surface with boundary, there are two ways to do this, because there always are two ways to pick a positive direction in a real line bundle. In the theory I'm describing to you, along the boundary of sigma, one is always given locally, away from punctures, a choice of trivialization of the spin bundle. But the rule is that this trivialization jumps in sign when one crosses a boundary puncture. With this rule, the number of boundary punctures on a disk has to be odd, because in the disk, you're in the Nevers-Schwarz sector, so the spin structure is antiperiodic. That means it can't be globally trivialized. So any attempt to piecewise trivialize it will involve an odd number of jumps in going around the disk. So there could be just one jump, or as drawn here, there could be 5. Well, finally, with this refinement of what you mean by MGNN prime H, anomaly cancellation is complete. And the orientation issues in defining the correlation functions are resolved. So I haven't shown you the technical computation to prove that, but there's no more problems of sign in defining the integral you're trying to do. But if you remember what we said about halfway through the lecture, there was another problem, which is that the moduli space is naively a manifold with boundary. And in general, you can't integrate a cohomology class on a manifold with boundary. However, there's a bit of magic. Once you require these local trivializations of boundary spin structures, the boundaries behave as if they're of real codimension too. And therefore, the integral becomes well-defined. And I'll just explain heuristically why this happens. So here's our disk, which has 5 punctures on the boundary. And now we've let a narrow neck degenerate, so the picture turns into this, which means that you've got 2 disks that were glued together by gluing P1 onto P2. And to the naked eye, it's impossible for sigma 1 and sigma 2 to both have an odd number of punctures, boundary punctures, because sigma had an odd number of boundary punctures, and an extra one appeared on each side at the degeneration. So no matter how the 5 you already had are distributed, one side will have an even number of boundary punctures, and one side will have an odd number of boundary punctures. But if this surface had piecewise local trivializations of spin bundles, then this is still true here, and it's still true here. But a local trivialization of a spin bundle will always have an odd number of jumps. So it must be on this surface. Well, we know we have a jump here and here because it came from this. There must be a jump at P1. On this guy, there are jumps here, here, and here, so there must be no jump at P2. So the instruction is to forget about P2, because the trivialization of the spin bundle isn't jumping there. Well, I skipped a lot of stuff that I explained on this slide. I'm not sure if I should take the time to explain it. What I mostly skipped was verifying that this degeneration happens in real codimension 1, so it is a boundary geometrically. It's a boundary just when this neck here shrinks to 0 size, as drawn. So if you think that the number of mark points on the boundary is supposed to be always odd, it tells you that you should be forgetting about P2. And technically, so once this is done, the boundary behaves as if it's of codimension 2, not 1. Technically, when we do an integral, we only allow a gauge transformation psi to psi plus d alpha if alpha restricted to the boundary is a pullback by the map that forgets one of the new mark points, the one that shouldn't be there. So in this situation, we require alpha not to depend on P2. And with the recipe that alpha can't depend on P2, your correlation functions become well-defined. That was a bit of a mouthful, possibly, so I hope you got at least something out of that last explanation. At any rate, in this talk, I've tried to give an overview of at least some of the approaches to two-dimensional gravity, and to tell you something about at least one relatively new development that's perhaps still not so well known. What's next? Well, I don't know, but I'm puzzled over the topological field theory interpretation, if any, of unorientable Riemann surfaces, which are straightforward to incorporate in the other two approaches. Thank you.